Okay, so in this short tutorial, what we're going to learn about is something called the rule of sum, or the additive counting principle. Again, this is something that we've previously done already, but we're going to see how this ties into factorials and permutations and things like that, and how we can solve, we're just adding complexity to the types of problems that we're able to solve. So for mutually exclusive actions, remember, these are actions that cannot occur at the same time. If one action could be performed in m ways and another in n ways and another in a third in p ways, then you simply add up the different ways that it can happen to get the total. Now, whenever we talk about mutually exclusive events, right, and we think about a Venn diagram, they don't overlap. We're also using the word or, so that's important that we use the word or, not the word and. The word and implies sort of multiplication. The word or implies the addition. So again, understanding that is very, very important. So imagine you're asked a question: in how many ways can you draw a 5 or a queen from a deck of cards? Okay, so that's something that's a good question. So first of all, you just ask, in a standard deck of 52 cards, how many 5s are there? Well, we know there's 4. So there's 4 cards, and it says or a queen from the deck, and there are only 4 queens. There we go. So they're mutually exclusive because there's no overlap. Alright? And why is it addition? Well, we can draw a 5 or a queen. So there's 8 possible ways of doing this. You would have already figured this out. Rather than calling it the rule of sum or the additive counting principle, you would have just said, well, there's 4 5s and there's 4 queens, so there's 8 possible ways of doing that from a deck of 52. So calculate the probability of drawing a 5 or a queen from a deck of cards. Well, the probability of a 5 or a queen is simply 4 plus 4 over 52, or 8 over 52, which you could put, if you wish, as a decimal. So we do 8 or 52, which is 0.154, or about 15% probability or chance. Okay, so let's look at a signal flag question. This is a standard type of question that people pose when they're doing these types of problems using the rule of sum. So sailing ships and ships in the past used to use flags, quite an intricate array of flags, in fact, for figuring out how to send messages. So if you have, there's 4 signal flags here, and it says here how many different signals are possible with a set of 4 distinct flags. So here's 4 distinct flags, for instance. And the question is, you must have a minimum of 2 flags for each signal, okay? And you can only use the flags once since there's only 4. So you really have an option of using just 2 flags. So how many ways can we select 2 flags? And the other way to look at it is and then you could use 3, or you could use 4 flags and then find out the total. Well, how many ways are there of selecting 2 flags? Since there are 4 distinct flags, the first option we have 4. Now we've used one of them, 3 left, so we use the fundamental counting principle to figure that out. We end up with 12. Okay, another way of doing this is you could have said 4p2, which is 4 factorial, because we want to say 4 but we're picking 2, over 2 factorial, which is 4 times 3. Now the 2 factorial over 2 factorial divide out, and you're left with 12. So you get the same answer. So you can use factorials, you can use the fundamental counting principle, whichever you wish. Okay, so for 3 flags, 4 times 3 times 2 is 24 possibilities. Again, you could simply just go 4p3, which we know is 4 times 3 times 2, or you can write in factorial notation whatever you want. That's still 24. And for 4 flags, another 24 ways of doing that. And again, that's 4p4, which is just 4 factorial, which is, again, 24. Okay, so you can use, like I said, the fundamental counting principle, factorials, permutations, to figure this out. So total number of flags, because you can use 2 or 3 or 4, the total number of flags, therefore, is 12 plus 24 plus 24, which of course is simply 60 possible signals. So with just 4 flags, using a minimum of 2, there are actually 60 possible signals you can make. Okay, so let's take a look at a different one here, the one at the bottom here. And the question is, at an international conference, either 8 or 9 countries may attend. How many arrangements of flags can be flown? So, since we're talking about how many arrangements of these flags can be flown, and there can be 8 or 9 countries involved, then what we are going to look at is, let's say that 8 countries fly their flags, okay? And how many arrangements can you arrange these 8 items? Well, if you have 8 items and you're taking all 8 of them, that's simply 8 factorial arrangements, which is quite a bit, okay? And again, we could have just done the fundamental counting principle and done 8 times 7 times 6, all the way down. Now, if 9 people show up, if 9 countries show up, and we take all 9 of them and we want to arrange them, there are 9 factorial ways of arranging them. So, the total number of arrangements is 8 factorial plus 9 factorial, which is 403,200 possible arrangements of the flags if you can have 8 or 9 countries show up. Okay, we'll look at a couple of ones on the back and go from there. Okay, so dealing cards. So this is going to be something called the principle of inclusion and exclusion. So let's say that we are dealing out cards to 3 players. Each player only receives 1 card. Fair enough. In how many ways could cards be all face cards? So I'll underline that. Or, again, there's the word or, all black cards. Order is important. So again, we're talking about arrangements of this happening. So we need to think about permutations since order is important. And that's because each player receives a different card from this. Now to help you visualize this, and again there's 3 players. To help you visualize this, if we draw a little Venn diagram here like this might help. There are face cards in the deck, okay, and there are black cards in the deck. Now, it turns out that there are also an overlap. There are black face cards. Okay, so now let's take a look at this. Let's figure out how many ways you could send out or deal out to these 3 players one of the face cards. So face cards, we know that there are 12 face cards and we're going to pick 3 of them. So we're going to deal 1 out to each of them. We could have done simply 12 times 11 times 10 to figure that out using the fundamental counting principle, or you can simply write it as 12p3. It's up to you when you're doing that. So just remember that this is exactly the same thing as 12 times 11 times 10, okay, or 12 factorial over 9 factorial, same thing. Alright, so what about black cards? Well, the black cards that are in here is 26p3. So there are 26 black cards and we're going to pick 3 of them. And again, remember that's just, there's 26 times 25 times 24 if you're using the fundamental counting principle, or 26 factorial over 23 factorial, which is the same thing as this. So now the problem is that there's some overlap. But how many overlaps are there? And that's the question. Black face cards. Well, it turns out that there are 6 black face cards. The Jack, the Queen and the King of clubs, and the Jack and the Queen and the King of spades. So out of those 6, how many ways can we arrange 6 of those cards if we're taking 3 of them at a time? In this case it's just 6 times 5 times 4, or 6 factorial over 3 factorial. So again, this is the number of arrangements of black face cards that could be dealt. This is the total number of arrangements of face cards, total number of arrangements of black cards, and the intersection of them. So using the principle of inclusion and exclusion that we learned before, the total number of ways where the order matters of doing this is 12p3, so the number of face cards, plus the number of ways of dealing out the black cards. But that and that added together does a double count, so therefore we need to subtract the number of ways of arranging the 6 black face cards. They're already counted in here because in both of these options it includes the black face cards twice. So we have to subtract it off once in order to figure it out. Putting this in your calculator, doing that plus that, subtract this, simply gives you 16,800 different ways that a player can receive a different card. Okay. You may want to pause that, rewind it, listen to it again. 3 players are dealt 1 card each. If order is important, in how many ways can this be all hearts? So again, 3 players are dealt 1 card each. So we say, well, how many hearts are there? There are 12 hearts, and we're picking 3 of them. That's it. And again, 12p3, if you want to put it in your calculator, it's just 12 times 11 times 10. 1320. Be all aces. Well, there's only 4 possibilities up for aces, and we're going to pick 3 of them. And that's just basically 4 factorial over, so 4p3 is 24. And you're like, well, how'd you get that? Well, there's lots of different ways. There's 4 times 3 times 2, which is 24, or you could do 4 factorial over 1 factorial, which is 4 times 3 times 2. It's all the same thing. It's 24. Okay, so how about it being all aces or hearts? So what we do is we say the total number of ways of dealing out all the hearts plus the total number of arrangements where order matters, where we're dealing out the aces. And it turns out that there is only 1 ace of hearts. So if we, in this here, this includes, since it says all hearts, this includes the ace of hearts in there somewhere. And this one here also includes the ace of hearts. So we've double counted it, so we can't have that. And so therefore what we need to do is subtract off 1, where basically it's 1 factorial if you will, but that's where there's only the 1 heart. And again, that's 1320 plus 24, subtract 1, so the answer is 1,343 is the total. Alright, the last example, and then we'll work on the problems that go with this. So lining up for a medal, the indirect method. So let's say that you have 12 people on a baseball team and they're lining up for the medals after a tournament. In how many ways can this be done? And the first option here is with no restrictions. Okay, well, if we're just lining them all up for medals at the end, it's going to be, I'll just use this notation just to show you that there's, it's 12 people and we're picking all 12 of them where order matters. And 12p12 is simply 12 factorial over 0 factorial, but we know 0 factorial is 1, so it's just 12 factorial. And we end up with a big number. There we go. 479 million approximately. Alright. What about if the captain and the assistant captain must be together? So one of the strategies here is to treat them as one. Okay, so that's one strategy. You've already been using the strategy in the other practice problems that you've been working on, but again, this is just to reiterate that this is a really, really good technique. So imagine we clump them together. So the captain and the assistant captain are right beside each other. The thing is that if they're one group now, and there were 12 people, we know that there's 10 people left to arrange. So that's 10 people plus their little group brings us back to 11. So if you imagine the 10 individuals, and then 2 of those people count as 1, we're now at 11. So there's 11 objects that we have to arrange around in order. Well, how many ways can we arrange 11 objects? Well, it's 11p11, so that's 11 factorial. But the point here is that the captain and the assistant captain could be captain then assistant captain, or the reverse, assistant captain and captain, for each of those positions. So how many ways can you arrange the captain and the assistant captain? There's 2 of them, and we're going to pick 2 of them. So it's 2p2. So really what we're saying is there's 2 factorial ways of arranging them, the captain and the assistant captain, and then to arrange 11 objects, because remember there were 10 separate plus the 2 together, is 11 factorial, and you end up with 7983360 79 million approximately, as you can see there. Another way of doing this that I've seen people do is they'll say, well, okay, I understand that the captain and the assistant captain must be together, and there's 2 factorial ways of arranging them, so everyone's fine by multiplying by 2. Then I see people multiply by 10 factorial to say, well, there's 10 objects they want to rearrange, but then they realize at that point that there's 11 different positions that grouping for the captain and the assistant captain can be in, so then they multiply it by 11. It gets you the same result, it's just a different way of thinking about the problem. Alright, if the captain and the assistant captain must not be together. Okay, well, let's just take the total number of ways of arranging them, all the people individually, and subtract when they are together. That's simply it. So we took part A, subtracted part B, and we get the result for how many ways, or sorry, how many arrangements there are where they are not together. And that makes sense because this contains the total, this contains a subset of that, and therefore what's left over is when they're not together. Okay, the very last one is this question here: in how many ways could the letters in the word factor be arranged so that the vowels are not together? Okay, so just take the word factor. There's no repeating letters in here, so that's good. So there's 1, 2, 3, 4, 5, 6. So there are 6 factorial ways of arranging the letters. You're like, okay, that's good, but some of those contain when the vowels, so it says arranged so the vowels are not together. And so what we just need to say is, well, let's subtract off the arrangements when they are together. So vowels together, and this is very similar to the problem above where we say, well, there are only 2 vowels in here, so there's 2 factorial ways of arranging those vowels, and then treat them as 1, and that's 1, 2, 3, 4, so there are 5 objects left to arrange. That's the the F, the C, the T, and the R, so that's 4 of them, and then the O and the A are together, so that's 5, and then how many ways can we arrange those? And then you multiply it by the AOOA ordering, and so that is when the vowels are together. So if we subtract off when they are together, then we get when they're not together. And again, putting that into your, so it's 720 for total number of arrangements, less the 240 when they are together, gives us 480 where they are not together. So if you want, that's the total, subtract together, and that gets you the not together. Okay, so that's the lesson for this, and what we're going to do is work through the additional problems that are on the website as well, and that are handed out in class. Thanks.